Hello, everyone. Good morning, afternoon, or evening, depending on where you are joining us from. So I'm Ada Halbig and will be the chair of the webinar today. And it's my great pleasure to introduce you to our speaker, who is Mehran Mazandarani. Hope I pronounced that correctly. So I'm just quickly going to first introduce him to you. So Dr. Mehran Mazandarani holds a Ph.D. in electrical engineering and specializing in control from the Ferdowsi University of Mashhad. He's an accomplished researcher who has worked in various capacities across different countries. From 2017 to 2018, he joined the Computational Mathematics and Engineering Division at Ton Duc Thang University in Ho Chi Minh City, Vietnam, as a researcher. Following this, he worked as a visiting researcher at the Harbin Institute of Technology in Shenzhen, China, from 2018 to 2019. As a postdoctoral researcher, he worked at the Department of Information Sciences and Technology at Tsinghua University in China from 2019 to 2022. Currently, he is associated with the Department of Mechatronics and Control Engineering at Shenzhen University in China. Dr. Mazandarani's research interest includes several branches of fuzzy logic, such as using fuzzy mathematics and control theory and introducing new frameworks in this area. He has made significant contributions to fuzzy mathematics. For instance, he introduced the concept of type 2 fuzzy differential equations, type 2 fractional fuzzy differential equations, so type 2 fuzzy calculus, and the idea of granular differentiability of fuzzy functions, which revolutionized fuzzy differential equations. In 2019, he developed a firm framework for studying Z calculus. Recently, he and his colleagues introduced a new approach in the field of imprecise mathematics that led to the introduction of the mother of differential equations. In addition, he has developed a new generation of fuzzy inference systems called fractional fuzzy inference systems, which have been demonstrated to outperform traditional fuzzy inference systems. This significant achievement has led to the creation of a new branch within the field of fuzzy inference systems. Currently, his research is focused on exploring the foundational principles of fuzzy logic, intelligent control systems, and complex systems of uncertainty and perception-based computations, as well as their potential applications in intelligent systems. Before I hand over to him, just a little bit of housekeeping. So if you have any questions for the speaker during the webinar, you can click on the questions pane. There you'll see a text box and you can type any questions there for him. Please take note that this is being recorded. And you also have handouts. So if you click on the handouts pane, you will see the files there and you will be able to download them. So with that, I'll hand over to you. Thank you, Mehran.
Okay. Hi there. First, I would like to thank you very much, Professor Helbig, for your introduction. I would also like to extend my gratitude to the organizers of this IEEE CIS webinar. Additionally, I'd like to express my appreciation to everyone who has attended this online session or will watch it offline. Today, I'm talking about a new branch of fuzzy systems that's called fractional fuzzy inference systems, or FFISs for short. So let's get started. First, I'd like to introduce some references related to the topic that we can use to learn more about the technical details of this new branch of fuzzy systems. Additionally, a video file has been published on YouTube that provides detailed information about the concepts related to the fractional fuzzy inference systems, along with a large number of simulations. Moreover, a MATLAB toolbox has been developed to enable more convenient simulation and programming code writing within the MATLAB software. This toolbox is also available for download through my ResearchGate webpage. Furthermore, a video tutorial on how to use the MATLAB toolbox in your simulation is available on YouTube. So here is the outline of this webinar. First, an overview of importance of FFISs is provided, followed by their effective impact on the current and future applications. Next, we will discuss some conceptual impressions related to the fractional fuzzy inference systems, and then some simulation examples are presented. Finally, the experience and observations related to the practical implementation of fractional fuzzy inference systems on the real-time position control of an LSRM carried out in the laboratory of the Department of Mechatronics and Control Engineering at Shenzhen University will be shared. Before we begin, I'd like to emphasize that the purpose of this webinar is to provide a concise and conceptual introduction to the topic of fractional FISs. Our focus will be on the broad range of effective applications and the positive impact on systems where traditional fuzzy systems have been used. My priority is to present the topic in a simple manner, accompanied by easy to understand examples. Okay, maybe it is expedient to start from this point that we assume that you've got a project, system, method, everything in which you've used a typical FIS, for example, Mamdani's fuzzy system. And this is the question on the table for which we're looking for an answer. Is it possible to improve the results of the project, system, or method without making any change in fuzzy if-then rules, membership functions, fuzzification method, defuzzification method, inputs, outputs, gains, and the general structure of the system? Actually, one of the main contributions of fractional fuzzy inference system is to provide an answer to this question, and the answer is positive. Let's approach this question from a different perspective. Suppose that you've got a system, method, or project in which you have employed a typical fuzzy inference system, such as Mamdani's FIS. If you want to enhance the results or outputs of your system, you can explore techniques such as optimization algorithms, learning algorithms, improving techniques in order to get more satisfactory results. Nevertheless, at the end, you arrive at the conclusion that there is no way to obtain more satisfactory results while all algorithms, techniques, optimization methods, and so forth have been applied. In other words, you still need a better result. Thus, in this situation, the question becomes, what shall we do? A common suggestion is to enhance the type of fuzzy systems and implement type 2 fuzzy systems, which may be viewed as a potential solution. However, this approach presents certain challenges, including using type 2 membership functions in antecedent and consequent parts, computational complexity. Inference block needs to be adapted with the type 2 fuzzy system, and adding type reduction compartment. However, our viewpoint here is that you should increase the range of the order of FIS rather than the type, and use the fractional fuzzy inference system. In fact, all you need to do is replace the compositional rule of inference with its corresponding fractional compositional rule of inference. Such a change involves modifying the way in which the system reasons to produce the output from first order reasoning to the fractional order reasoning. Therefore, in this perspective, the only difference in the configuration of fractional fuzzy inference systems and that of typical fuzzy inference systems is related to the order of inference mechanism. And only this part, inference mechanism, or more concretely, the reasoning mechanism, needs to be modified. Thus, all other parts are the same for both fuzzy systems. Therefore, to provide a brief answer to the question of when and why we should utilize fractional fuzzy inference system, we can say that it is to achieve more satisfactory results, or when you would like to get better results without increasing the type of fuzzy systems, or when there is no way to improve the results, or to obtain more satisfactory results without making any change in the surface structure of fuzzy systems. And above all, if you want to increase the accuracy while the interpretability is retained. Based on the theorems presented in the original papers, it's been demonstrated that, independent of the problem, a typical FIS never leads to more satisfactory results than its corresponding FFIS does, provided that the order of FFIS is adjusted suitably. Perhaps for certain reasons, one may insist on using type 2 fuzzy systems and desire to improve the results. For this reason, the fractional inference mechanism has been extended to the context of type 2 fuzzy systems. As you may know, type 2 fuzzy systems have been introduced with some concepts, namely lower and upper membership functions, based on which footprint of uncertainty is defined, type reduction, and embedded fuzzy sets. Nevertheless, the newly proposed type 2 fractional fuzzy inference systems presented in 2022 come with more than 10 uniquely new concepts, such as interval type 2, fractional membership functions, type 2 fracture index, the concept of switching, the concept of entanglement, the degeneracy concepts, and so forth. Therefore, based on theoretical demonstrations, we can conclude that, independent of the problem, typical type 2 fuzzy inference systems never yield more satisfactory results than type 2 fractional fuzzy inference systems. Hence, in this perspective, fuzzy inference systems may be categorized into two groups: traditional fuzzy inference systems, which originated from seminal works dating back to around 1975 and may be viewed as first-order fuzzy inference systems, and a new group known as fractional order FISs, which represents a new branch of fuzzy inference systems. Thus, to sum up this section, I would say that if there is a system, project, method, or anything in which you have employed a typical fuzzy inference systems, if you replace the typical fuzzy inference system with its corresponding fractional FIS, then you can get more satisfactory results. You may have a model with more accuracy, a control system with higher performance, and a lower error in your prediction, and eventually intelligent system with higher IQ. So let's go into the second part. As a first example, let's start with the Sendai subway, the world's first train that uses fuzzy systems. If fractional fuzzy inference systems are used instead of the fuzzy system in this train, then the energy efficient certainly increases. Now, some examples in consumer products are given. Let's start with cameras. Cameras have several focusing spots and use fuzzy-if-then rules to calculate the optimal focus. They also use fuzzy systems for image stabilization. Thus, the quality of cameras can be improved by replacing the fuzzy systems used in those products with fractional fuzzy inference systems. In fact, there have been numerous techniques in the field of image processing that use fuzzy systems for edge detection, stabilization, and image enhancement. Many papers in this area have applied typical fuzzy systems, for example, Mamdani's fuzzy system. Therefore, informally speaking, better results can be obtained by applying fractional fuzzy inference systems instead of the typical fuzzy inference systems. Another example of consumer products that employ fuzzy systems is rice cookers. Companies like Breville and Philips utilize fuzzy systems in the rice cookers, which have earned them a spot on the list of the best rice cookers available. The superior quality of these rice cookers is a testament to the effectiveness of fuzzy systems in improving their performance. In fact, the use of fractional fuzzy systems in the control structure of these products could significantly enhance their quality and performance even further. Based on information dating back to 2014, Omron company has sold approximately 120 million blood pressure measuring machines, totaling $12 billion in revenue. This type of machine utilizes fuzzy systems. If fractional fuzzy inference systems are employed in this product, accuracy and performance can be improved. It is possible for a company to register a patent for the application of fractional FISs in pressure measuring machines and to produce such machines, leading to a successful business venture and potential wealth. It's important to note that the general structure of the hardware and sensors used in these products needn't be changed with this improvement, as the surface structure remains the same as before. Washing machines use sensors and fuzzy systems to detect the level of dirtiness and the speed of water clearing, which helps determine the optimal length of wash cycles. It is worth noting that employing fractional fuzzy inference system can improve the performance of these machines. For example, by reducing energy consumption and increasing the energy efficiency index. Those who are interested in control systems and control theory might be familiar with the applications of fuzzy inference systems in control. This is the basic and yet important structure in which the fuzzy inference system plays the role of a controller. So more satisfactory results can be achieved if you replace the typical or first order inference mechanism with the fractional order inference mechanism. So this can be considered as a new topic. Here, before continuing, I would like to highlight what I mean by getting more satisfactory results. As a simple example, consider this control system structure in which fuzzy system plays the role of a controller. And if you use this fuzzy system in order to control this plant, and assume that you have used Mamdani's FIS, and this is the response of the system, the blue curve. So if you replace the Mamdani's FIS with its corresponding fractional FISs, then by getting more satisfactory results, I mean that the response of this closed loop system would be one of these curves. Fuzzy systems are also used in a combination with PID controllers in order to get desirable results, even for some deviations or uncertainty in the plant parameters. Needless to say that all the works in which such a structure has been applied can be revisited by obtaining more satisfactory results. Meanwhile, fuzzy systems also serve as a means for alleviating or reducing the chattering image in the output when a sliding mode controller is applied. So using fractional fuzzy inference systems instead of the typical fuzzy inference system in this structure results in less chattering. In addition, FFISs can prove their effectiveness in the control structures in which adapting sliding mode controller have been applied. Each year, a large number of patents are registered by companies, institutes, inventors, and researchers around the world for their products or technologies that employ fuzzy systems. One example in this regard is the patent registered by the Dexcom company and published in 2022. It is about a product related to the management of blood glucose levels in diabetic patients. The controller predicts blood glucose levels based on the received data and generates control signals. In this structure, a fuzzy system was employed. So if the fuzzy system is replaced with a fractional fuzzy inference system, then certainly the accuracy and performance of the company product are improved significantly. This is another instance from the Evoqua Water Technologies company. This patent is about a system that cleans contaminated air. This system also has a controller that uses fuzzy logic to manage the process. The controller helps to make sure that the air is cleaned effectively. Thus, this is another situation where the fractional fuzzy inference system could be used instead of the current fuzzy system. If this replacement is made, the new products of this company will certainly perform better. In fact, there are hundreds of other patent cases published recently in which typical fuzzy systems have been employed, and these products can be enhanced if fractional fuzzy inference systems are applied instead of typical fuzzy systems. For example, here, this is a case from Bosch company, and this patent has been published in 2019. The patent is about a method and control unit for adapting a steer-by-wire system in an automobile, something like that. So all in all, there are many other subjects in which one may use fractional fuzzy inference systems. For example, in Internet of Things, in decision support systems, and above all, in fuzzy clustering and classification. And there are other subjects, for example, in fuzzy modeling, psychology, in emotion categories, multi-objective optimization problems, and so forth. And actually, in all the areas where typical FISs have been applied since 1975, those FISs can be replaced by FFISs, which leads to more satisfactory results. So let's start the third part, conceptual impressions. In our daily life, we almost always make a decision based on a relationship between the quality and quantity that is implicit or explicit in our goal or the task we are going to do. Such a relationship often is made unconsciously in our mind. As the first simplest example, let's see this conversation. Person A has asked person B about the price of the mobile phone, to which person B has responded, I bought it for about 1,600. Person A has expressed surprise at the high price, saying, "It's too expensive. Why did you pay for it?" Person B has then responded that the phone was worth the investment, indicating that they believe the quality or value of the phone justified its cost. Person A's question and person B's response suggests that they were evaluating the implicit relationship between the quality or value of the phone and its cost, which is a common decision-making process in daily life. Therefore, the such a relationship may also be postulated as an approximate structure of the reasoning mechanism, actually fractionalism reasoning, that in the mentioned case determines how much we are willing to pay for a product based on our evaluation of its quality or value relative to its cost, as exemplified by person B's reasoning that the mobile phone was worth the investment despite its high price. Some simple examples in this regard are reading a book, watching a movie, investing in a project, and so forth. Let's briefly take a look at one of these examples, reading a book. Intuitively, we read a volume of a book or a magazine for as long as it is informative. In other words, we read as many pages of the book as our mind values the book. In this case, our mind often unconsciously makes a relationship between the value and the volume of information included in the book. This relationship can be considered as a monotonic function in our minds, which may be also postulated as an approximate structure of the reasoning mechanism that determines how many pages of the book we should read. This also applies to preparing a tutorial, we spend time preparing a tutorial for as long as it is valuable. Here is another example that illustrates the relationship between the value and volume of information, the media's propagation and reporting of news. We receive a great deal of news and information through various media channels in our everyday lives, such as radio, television, and newspapers. The news conveys information, and the value of the news is directly related to the value of information it contains. The value of the news or information plays a significant role in determining both the volume of news that should be propagated and the amount of time that should be devoted to reporting the news of information. For example, suppose an event occurs in a city and the media report on it. If the news is considered unimportant due to its low value, it will be spread with low volume and may only be limited to the border of a country or neighboring provinces. If the news is deemed important, then the value of information conveyed by the news is high. Thus, the volume of news or information propagated by the media increases. This may include reporting on the news in other countries. If the news contains highly significant information, then the volume of news and information disseminated by the media increases substantially. So naturally, there is a relationship between the value and volume of information in reality and our lives. So the question is, what would happen if there were no effective relationship between the value and volume of information? Let's first examine the media example, where we suppose that the value of news or information does not effectively affect the volume of its propagation. I mean, no effective relationship is considered between the value and volume of information in the media. In this scenario, the media reports news continuously on all platforms, regardless of its value. This means that both important and unimportant news is broadcasted across all media channels. In the case of reading a book, let's suppose that our mind does not effectively relate the value and volume of information when reading a book. In such a scenario, if we conclude that the book is not informative enough, I mean, its value is low, we may still feel compelled to read all the pages. However, fortunately, our minds naturally establish an effective relationship between the value and volume of our goal. Such observations help us briefly express the principal rule in fractional fuzzy inference system. Informally, the principle of inference mechanism in fractional fuzzy inference systems is to maximize the utility of information by extracting a portion of its volume or exploiting the relationship between the value and the volume of information, with an emphasis on the maximum exploitation of available data. This mechanism is based on the reasoning that may be called fractionalism reasoning. Actually, the fractionalism reasoning suggests that exploiting the maximum volume of information does not necessarily imply the maximum exploitation of the information. Let's take a look at a simple example in this regard. Suppose that a journal invites you to review a paper, but only provides the abstract, which contains a fraction of the information. In this case, you need to reason and make a decision based on this limited information about whether or not to review the paper. It is important to note that your reason and decision should be based on exploiting a fraction of the information provided to you about the paper. What I'm getting at is, often we don't need the entire volume of information to make informed decision or to reason. Now, one may ask how such a mechanism is established in fractional fuzzy inference system. In the framework of fractional fuzzy inference systems, a fuzzy set is regarded as a carrier of information. This viewpoint prompts us to consider not only the value, but also the volume of information contained in the fuzzy set. Thus, the relationship between the value and the volume of information becomes a significant factor in making decisions based on the given information. In the theory of fractional fuzzy inference systems, the value of information is linked to the truth degree coming from the antecedent part of a fuzzy if-then rule. Consequently, we introduce the mu star, the truth degree coming from the antecedent part, to represent the value of information. The alpha star stands for the volume of information, and the alpha star is also called the fractional index. The function f connects the mu star to the alpha star, determining the form of relationship between the value and volume of information. For example, this is the linearly simplest relationship between the value and volume of information. Thus, in this setting, if the value is equal to 1, then the entire volume of information is utilized in decision-making process. And if the value decreases, then the volume also decreases linearly. Alternatively, if the value increases, then the volume increases linearly. So let's take a look at the behavior of a typical fuzzy inference system based on such a viewpoint. In this analysis, we will examine the behavior of a typical FIS that includes only one single fuzzy if-then rule for the sake of simplicity. I mean, fx is A, then y is B as the major premise of the inference query, and x is x naught is the input of the system or the minor premise of this inference query. Furthermore, for simplicity, the minimum operator has been chosen as the base operator in the joint constraint on the variables x and y. In this case, the fuzzy set denoted as B prime represents the output of the FIS. Besides, it is highlighted by the green region and obtained by the compositional rule of inference, CRI. Thus, according to the viewpoint mentioned in the previous slides, we can observe that the value of information changes while the volume remains constant. Additionally, the resulting fuzzy set contains the maximum volume of information independent of its value. Technically, here, the alpha star, the fractional index, is always equal to 1. I mean the unity. So we may conclude that in typical fuzzy inference systems, a maximum volume of information is extracted for making a decision. There is no effective relationship between the value and volume of the information in the process of making a conclusion, in the sense we have already explained. Moreover, the behavior of typical FIS is similar to that of the media, where no effective relationship between the value and volume of information is considered. However, for making an intelligent decision, not only the value, but also the volume of information should be considered. And this is what comes true in fractional fuzzy inference systems, where the inferred fuzzy set B prime conveys information in which an effective relationship between the value and volume of data exists. Note that here we have considered a linear relationship between the value and volume of information. Note that here the fuzzy set B prime is inferred through the application of the fractional composition rule of inference, FCRI. So let's take a look at the simulation. In the simulation, we consider a simple linear relationship between the quality and quantity in the FFIS, which can be seen as an approximate model of the reasoning mechanism. And based on this model, the inference fuzzy set B prime, which serves as the output of the FIS, is justified. So on the left-hand side, you can see the fuzzy set A in the antecedent part. On the right-hand side, you see two windows. The upper one shows the output of the FFIS highlighted by the green region, and the lower one is the output of the typical FIS. That is, in fact, here it is the Mamdan is FIS. So we can consider any relationship between the value and volume of information. Let's go into the fourth section and see some more examples. Here we have considered a fuzzy system including only one single fuzzy if-then rule, and A and B are fuzzy sets in the antecedent and consequent part respectively. The falsifier is singleton, the defalsifier is centroid, and the basic rule of inference is the composition rule of inference. The base operator for the joint constant on the variables x and y has been considered as the minimum operator, and the input is x naught, which varies from 0 to 2, and we have also considered the same structure for FFIS, and the only difference between the FFIS and the previous one, the typical FIS, is the reasoning mechanism or inference mechanism. Moreover, all the simulations have been done based on the main file in the MATLAB toolbox. As I have mentioned in the previous slides, we can consider a variety of functions to approximate the model of the reasoning mechanism, assigning the desired function to the alpha star, the fractional index. Here you can see some of such functions. Note that in the typical FIS, the alpha star is always equal to 1, I mean the unity. In fact, the reasoning mechanism in human minds might be incredibly complex and varies from person to person. Thus, it can be difficult to model mathematically. However, fractionalism reasoning mechanism that is central to the fractional fuzzy inference system provides us with the use of many different functions through which we might create a more flexible and adaptable model that can better approximate the complex structure of the reasoning mechanism. Thus, this variety of functions is beneficial because it allows us to discover and analyze the many different types of reasoning mechanisms from fractional order. So let's examine one of these functions. The sinusoidal function. I would like to highlight that in the center, the upper window shows the output fuzzy set coming from the FFIS, and the lower one shows the output fuzzy set of the typical FIS. On the right-hand side, you will see one single window. The blue curve shows the defalsified output of the FFIS, and the red curve shows the defalsified output of the typical FIS. So the point about this example is that we can obtain different fuzzy sets and outputs from the fractional FIS, while its surface structure is as the same as the typical FIS. This means that the space of the fuzzy system output has been greatly expanded, allowing us to discover solutions that were previously undiscoverable using typical FISs. Let's consider fuzzy systems with two fuzzy if-then rules. Here, A sub 1 and A sub 2 are fuzzy sets in the antecedent parts, besides B sub 1 and B sub 2 are fuzzy sets associated to the consequent part. And this structure is the same for both fuzzy systems. I mean, fuzzifier, fuzzy if-then rules, membership functions, defuzzifier, everything. The surface structure is the same for both fuzzy systems, and the input varies from 0 to 3. The point about this simulation I would like to highlight is that so far as you have observed, the output of the FFIS has been different from that of the typical FIS, despite having the same structure. In this simulation, I'd like to emphasize that the output of the FFIS converges to that of the typical FIS, and the order of the FFIS approaches 1. Note that the typical FIS is a first order FIS. When the order of the fractional FIS approaches unity, the 1, its output approaches that of the first order FIS. I mean, the output of the typical FIS. For more information on the concept of FIS order, please refer to the tutorial published on YouTube. In the simulation, the initial order of the fractional FIS is equal to 0.45. And we gradually increase the order of the fractional FIS. Technically, here, let me show it to you. Technically, here, actually, in this case, the order is equal to the half of the sum of these two numbers, So let's start. And again, on the right-hand side, the blue curve shows the defuzzified output of the fractional FIS, and the red dash curve shows the defuzzified output of the typical FIS. And this lower window collects the outputs of two fuzzy systems. So now the order increased again 0.55, 0.6, and as you can see, the output of the fractional FIS shown by the blue curve approaches the output of the typical FIS. As the order of the fractional FIS approaches the 1. Now the order is 0.9, the order of the fractional FIS. And we know that the order of the typical FIS is always equal to 1. And when the order, let's pause here, and when the order of the fractional FIS is equal to 1, as you see, the output of the FFIS coincides the output of the typical FIS. We have compared also the performance of an FFIS with a typical FIS, specifically Mazandarani's FIS, for the control of an inverted pendulum system whose nonlinear mathematical model has been shown here. The objective of the control is to track the predefined reference, and this is the reference. As you see, the system under the Mazandarani's FIS has become unstable. However, This is stable, and the reference could be tracked by the use of FFIs from different orders. So without making any change in the surface structure, the system now is stable. Let me explain one more point about this system. Note that both systems have the same surface structure. This observation shows that fuzzy inference systems from fractional order has a great potential than the first order FISs to stabilize systems and enhance the robustness. In fact, in the published papers, we have also shown how effective FFIs is in the improvement of the robustness in comparison with the type 1 and type 2 fuzzy system, while the structures of two systems is the same. So now let's start the final part. So I'd like to share with you some of the results of the practical implementation of an FFIs for the real-time control of the LSRM. Actually, an LSRM is a typical direct drive linear motor with a variety of applications such as in transportation systems, wind energy systems, medicine, so forth. The windings are fixed on the stator core. When three-phase windings are supplied by enough energy, the electromagnetic thrust pushes the mobile part into the right or to the left. Here, the position of the LSRM should track the predefined reference, which is in the form of a sinusoidal wave function. So our aim was to compare the performance of the fractional FIS with Mamdani's FIS under the same setting, the same structure. The control objective, as mentioned before, was the position control of the LSRM to track a predefined reference. And the reference here is a sinusoidal function. When its amplitude is positive, the mobile part moves to the left, and when its amplitude is negative, the mobile part moves to the right. In this experiment, the hardware components of real-time controllers were based on a speedboat platform connected to a computer and current drivers. For the software aspect, we utilized the MATLAB environment with the Simulink toolbox to interface between the software and hardware. In order to show the results of this experiment, we recorded the computer screen online. What you are watching now is a playback of this recording. So let's play it. First, a typical fuzzy controller, the Mamdani's fuzzy controller, is applied in the closed loop control systems, and you are watching the reference and the actual output of the LSRM that is detected by a magnetic sensor. The actual position of the LSRM is the red curve, and the blue curve is the reference. Actually, since these two trajectories are very close to each other, it is expedient to examine the error between the actual position of the LSRM and the reference position. Because by analyzing this error trajectory, we can effectively assess the performance of both controllers. And I frequently toggle between two controllers to compare their performance. Now, in the real time, switch to the FFIs, and this is the error of the system, the difference between the actual position of the LSRM and the reference. And now the FFIS is in the closed loop system. So you can see the effectiveness of the application of the fractional fuzzy inference systems. So again, yes, now again we switch to the typical FIS, and what you are watching now is the error that has been obtained by the application of the typical FIS. And again, now we switch to the fractional fuzzy inference system, and now FFIS is in the closed loop control systems. So our observation was that by the use of FFIS instead of typical FIS, we could obtain about 70% improvement in the accuracy of the control objective. So as you see, we could obtain a more accurate position control while the surface structure between two systems have been the same. I mean, the fuzzy if-then rules, membership functions, inputs, outputs, everything has been the same between these two systems, but we could get more satisfactory results, 70% improvement. So as a final, I would like to emphasize that actually, due to short time, I wasn't able to talk about many other concepts related to the FFIS, among which are the left and right orders, touch points, fractional membership functions, operating modes, and entanglement, and many other concepts. Thank you so much for your attention, and if you have any questions, please feel free to reach out to me by email.
Thank you very much, Mehran. So I just see that here are two questions from the audience. So the first one, thanks a lot, Professor Mazandarani, for the presentation. May I ask you, what is the difference between your fuzzy system, so fractional fuzzy systems, and intuitionistic fuzzy systems?
Actually, here by the typical fuzzy inference system, I mean that fuzzy inference systems are there are many fuzzy inference systems, and the classical fuzzy inference systems in which the classical fuzzy sets are employed. Intuitionistic fuzzy inference systems, as you highlighted, hesitant fuzzy inference systems, and the other fuzzy inference systems. In intuitionistic fuzzy inference systems, actually, the intuitionistic fuzzy sets are used. So, and if you use, for example, hesitant fuzzy inference systems or type 2 fuzzy inference systems, the differences between these fuzzy inference systems comes from the difference on the surface structure of these fuzzy inference systems. One of them uses intuitionistic fuzzy sets, the other uses type 2 fuzzy sets, and maybe another one uses hesitant fuzzy sets, but they are all from first order. I mean, so intuitionistic fuzzy inference systems is categorized in the group of the first order fuzzy inference systems. And maybe it can be considered as an idea to introduce, to extend the order of intuitionistic fuzzy inference systems from first order to the fractional order. So as we have in the first group, first order fuzzy inference systems, it means that the classical fuzzy inference systems, type 2 fuzzy inference systems, hesitant fuzzy inference systems, intuitionistic fuzzy inference systems, and they are all in the first group. And we have the second group, the fractional order fuzzy inference system. And this is the difference between the FFIs and the classical fuzzy FIS, the typical by typical fuzzy FIS, I mean that actually also it also includes intuitionistic fuzzy inference systems.
Great, thank you. Then the second question, thank you very much for your presentation. Could you please explain the application of fractional fuzzy inference systems in machine learning methods? And also, may I contact you for my PhD dissertation because I would like to apply this method?
Actually, one of the main contributions of FFIs can be highlighted in combination with a machine learning method. As you may know, if a typical fuzzy inference system is combined with a machine learning method, then by the machine learning method we can train the system to adjust the parameters related to the surface structure of the system. So a combination of FFIs with a machine learning methods leads to an intelligent system that not only incorporates the expert opinion to understand how to do the task, but also it learns how to reason for performing the task better than before. And this is one of the key features of the FFIs in combination with a machine learning method. So by machine learning method, we can design an intelligent system which can learn how to reason, and it is not possible for the first order fuzzy systems.
Great, thank you, Mehran. Then just with regards to contacting you, if anyone from the audience wants to reach out to you, what would be the preferred email address that you want them to use?
So my email address, yes, I can write it here. So
if you could put it in the chat, then everybody can see that, or yeah.
Yes. And if there's any question, or yes, actually I forgot to answer the second part of that participant. Yes, I'm available, and you can easily reach out to me by this email, and I would be glad to help you.
Great, thank you. So then there's just also another comment from the audience where they just want to say thank you, very nice presentation. So then also from my side, so if you have any questions, So anyone in the audience, you can use the email that Mehran has put there to reach out to him. So feel free to contact him if you have any further questions, or you also want to ask him anything about this topic. And then also from my side, I would like to thank all of you for coming to this webinar. You were a great audience. And also I would like to thank our wonderful speakers. So Mehran, thank you so much for making the time and also for doing the presentation.
I appreciate it. Have a lovely, I appreciate it. I appreciate it.
Thanks.
Take care.
And then because this webinar is being recorded, you will have access to the recording as well as soon as it's made available. And also remember that you do have access to those handouts that you can download by clicking on the handouts pane. So from our side, thank you very much, everyone. And I hope that you have a lovely rest of your day, wherever you are in the world. And thank you very much for attending. Bye.